Hi friends, now we are going to introduce the concept of an analytic function. A function f of the complex variable set is analytic at a point z0 if it has a derivative at each point in some neighborhood of z0. In other words, f is analytic at z0, f analytic at z0 if its derivative exists not only at z0 but also at each point z in some neighborhood of z0. If f is analytic at a point z0, it must be analytic at each point in some neighborhood of z0. We have definition: a function f of the complex variable set is analytic, or we can say regular or holomorphic in an open set if it has a derivative at each point in that set. If we should speak of a function f that is analytic in a set S which is not open, it is to be understood that f is analytic in an open set containing S. We have f z is equal to z square. For an example, f z is equal to z square is analytic everywhere. Next, suppose we have f z is equal to mod z square. It is not analytic at any point since its derivative exists only at z is equal to 0. Only the point z is equal to 0 and not throughout any neighborhood. For reference, we have examples 3 and 5 in the session 4. If f z is equal to z square is not analytic at z is equal to 0, though its derivative exists there. The reason is that it is not possible to find a neighborhood of 0 such that the derivative of f at each point in that neighborhood exists. Next, we have an entire function. An entire function is a function that is analytic at each point in the entire complex plane. So, next we have a theorem, that is, if p is a polynomial in set of degree n greater than or equal to 0 given by, we have pz. As a polynomial, we can write pz is equal to a0 plus a1 z plus etc. plus an z raised to n, where of course we have an not equal to 0. Here n is always greater than or equal to 0. Then p is differentiable at all points z and p dash z is equal to p dash z is equal to a1 plus 2a2 z plus etc. plus here we have n, last term n an z raised to n minus 1, where of course an not is equal to 0. Proof: for n is equal to 1, 2 etc. up to n, we have limit h tending to 0 z plus h whole raised to n minus z raised to n by h, we can write as, that is, limit h tending to 0 z plus h whole square, not whole square, it is whole raised to n, minus z raised to n power n divided by h is equal to, again, limit h tending to 0, we can write z plus h whole raised to n minus z raised to n as, it is z plus h minus z plus h minus z into Z plus H whole raised to n minus 1 into Z etc. plus the last term we have Z raised to n minus 1 and whole divided by what? H. Since we have the formula a raised to n minus b raised to n is equal to, using that formula a raised to n minus b raised to n is equal to a minus b into a raised to n minus 1 plus a raised to n minus 2 into b plus etc. plus b raised to n minus 1. This is equal to limit h tending to 0. This I can split as limit h tending to 0. First term is Z plus H whole raised to n minus 1. Z plus H whole raised to n minus 1 plus Z plus H whole raised to n minus 2 into Z plus etc. The last term is Z raised to n minus 1. This I can write as, this is our n Z raised to n minus 1, n times Z raised to n minus 1. Thus, P dash Z, thus I can write P dash Z is equal to, limit h tending to 0, usual definition P of Z plus H minus P of Z by H. This is equal to, using this I can write this is equal to a1 into h tending to 0, first one a1 into limit h tending to 0 Z plus H minus Z by H plus next term plus etc. plus the last term we have an again limit h tending to 0, what we have Z plus H whole raised to n into n minus Z raised to n whole divided by h. This is equal to, we can write which is equal to a1 plus 2a2z plus etc. plus we have n Z raised to n minus 1. Next we have an example of polynomial function. By the previous theorem, derivative of a polynomial exists everywhere and hence it follows that every polynomial is an entire function. In particular, 1 Z, Z square etc. up to Z raised to n. This 1 Z, Z square etc. up to Z raised to n and the polynomial Pz is equal to, a naught plus a1z plus etc. plus an Z raised to n. Here we have capital N. an Z raised to n, of course an not equal to 0 are analytic functions. Next we have a rational function example. The quotient of two polynomials Pz and Qz, that is Fz is equal to Pz by Qz, where we assume that common factors of P and Q have been cancelled, is called a rational function. This function is analytic except at the points where Qz is equal to 0. For Qz is equal to 0, it is not analytic. Next we have a definition. That is, if a function fails to be analytic at a point Z0, but is analytic at some point in every neighborhood of Z0, then that Z0 is called a singular point or singularity of F. It is very important. Singular point. Next we have an example. We know that d by dz of z raised to n is equal to n z raised to n minus 1. This we have already discussed. D by dz of z raised to n is equal to n z raised to n minus 1. When n is negative integer, provided z not equal to 0. In particular, with n is equal to minus 1, the function fz is equal to n is equal to minus 1, the function fz is equal to 1 by z, or z not equal to 0. Has derivative, we have the derivative of 1 by z is equal to minus 1 by z square. Hence, f is analytic at every point except for z is equal to 0, where it is not even defined. Hence, the point z is equal to 0 is the singular point. Here z is equal to 0. For fz, here it is z is equal to 0 is the singular point. Next, we have an example. Fz is equal to mod z square. It has no singular point since it is nowhere analytic. We have necessary condition for analyticity. A necessary condition but not sufficient condition for a function f to be analytic in a domain D is clearly the continuity of f throughout D. Satisfaction of the Cauchy-Riemann equations is also necessary but not sufficient. The following example illustrate this. Sufficient condition for analyticity in D will be discussed in later chapters. Now, we have to show using two-path test that the function fz is equal to f of x plus iy, which is equal to square root of new function square root of mod xy, is not analytic at the origin, even though Cauchy-Riemann equations are satisfied at that point. We write the function as fz is equal to uxy plus I into vxy, which is equal to, I can write this as square root of mod xy plus I0. So that my uxy here it is square root of mod xy, and what about vxy? Here vxy is equal to 0, of course. At the origin, dou u by dou x is equal to we have dou u by dou x is equal to limit extending to 0 u x0 minus u00 by x, which is equal to what? Limit extending to 0, we have 0 minus 0 by x. So, this is again equal to 0, and dou u by dou y, we can write limit y tending to 0 u0y minus u00 by y. Here we have dou u by dou y. So, it is u0y minus u00 by y, which is again it is a limit y tending to 0, 0 minus 0 by y, which is again equal to 0. Similarly, we have dou v by dou x is equal to 0, dou v by dou x is equal to 0, and also dou v by dou y is equal to 0. at the origin. Hence, Cauchy-Riemann equations are satisfied at the origin. If possible, suppose f is differentiable at 0. It means that f dash 0 is equal to f dash 0 is equal to limit z tending to 0 f z minus f of 0 by divided by z, which is equal to limit z tending to 0. We have square root of mod xy minus f of 0 divided by x plus iy. Now, let z tending to 0 along the path y is equal to mx, that is through the path y is equal to mx, that is f dash of 0 is equal to, we have limit z tending to 0 square root of x into mx, that is here we have y is equal to mx square root of here mod x into mx minus 0 divided by x plus iy. Instead of y, I can write x plus I into mx, which is equal to limit z tending to 0, I can take x outside, x into square root of mod m divided by x into 1 plus im. This is equal to limit z tending to 0, square root of mod m divided by 1 plus im. I can cancel this x and x. So, it is square root of mod m by 1 plus im, which is equal to what? Which is equal to again square root of mod m by 1 plus im. This limits depends on m, and so it is not unique. So, f z is not differentiable at z is equal to 0. Hence, f z is not analytic at the origin. We have some rules of analytic functions. The derivatives of the sum and product of two functions exist wherever the functions themselves have derivatives. Thus, we have the following results. One theorem: if two functions are analytic in a domain D, their sum and product are both analytic in D. Next, we have the quotient of two functions is analytic in D provided the function in the denominator does not vanish at any point in D. In particular, the quotient Pz by Qz that is the quotient Pz by Qz of two polynomials is analytic in any domain throughout which what? This Qz not equal to 0. Composition of two analytic functions is analytic. More precisely, suppose that a function fz is analytic in a domain D and that the image of D under the transformation W is equal to fz. Fz is contained in the domain of definition of a function GW then the composition G f of z, that is here we have the composition G of f of z. G of f of z is analytic in D and it has a derivative d by dz of the composition G f of z, which is equal to G dash f of z into f dash of z. The proof of the above follows from the chain rule for the derivative of a composition function. Next theorem is that if f dash z is equal to 0 everywhere in a domain D, then fz must be constant throughout D. We can write fz is equal to, that is, we can write this fz is equal to uxy plus I into vxy. Uxy plus I into vxy. Mark it as equation number 1. If the function is differentiable at the point z0, using formula for obtaining derivative, we have f dash z0, which is equal to ux x0 y0 plus I vx into x0 y0. Equation number 2. By the assumption f dash z is equal to 0 for any z in D, hence from equation 2 we have for any xy in D we have ux plus I vx is equal to 0. That is, here it is equal to 0. Also by the Cauchy-Riemann equation we have what we have, ux is equal to vy and also uy is equal to minus vx. 3 gives vy minus, so 3 gives vy minus iuy is equal to 0. By using this equation from 3 we get vy minus iuy is equal to 0. We can write it as equation number 4. From this 3 and 4, equating real and imaginary part, we obtained ux is equal to, ux is equal to uy, which is equal to vx, again which is equal to vy, which is equal to 0 at each point in D. Next we show that uxy is constant along any line segment L extending from a point P to a point P dash and lying entirely in D. That is, here we have a figure P, P dash, Q, U, L, S. This is our domain D. This is of course our x axis and this is our y axis. That is, let S denote the distance along L from the point P, and let U denote the unit vector along L. That is, here U is the unit vector. It is along L in the direction of increasing S. We know from calculus that the differential derivative, that is du by ds, can be written as the dot product as du by ds is equal to, we can write this is equal to grad u dot u. This is our unit vector u. Mark it as equation number 5 from calculus, where grad u is the gradient vector, or we can say grad u is equal to, which is equal to dou u by dou x into I plus dou u by dou y into j, which is equal to uxi plus uyj. Mark it as equation number 6. So, the fact that ux and uy are 0 everywhere in D implies that grad u is a 0 vector at all points on L. Hence, it follows from equation number 5 that the derivative du by ds is 0 along L, and this means that u is constant on L. Finally, since there is always a finite number of such line segments joined end to end connecting any two points P and Q in D, the values of u at P and Q must be the same. We may conclude then that there is a real constant A such that uxy is equal to A throughout D. Similarly, vxy is equal to B, and it follows that we can write fz is equal to what? A plus ib at each point in D, that is fz is a constant throughout D. Next example, verify analyticity using differentiation formula, that is fz is equal to z square plus 4 by divided by z square minus 3 into z square plus 1. This is our solution, that the quotient, this fz is equal to z square plus 4 by z square minus 3 into z square plus 1 can be written as fz is equal to z square plus 4 divided by, I can use the formula a square minus b square is equal to a plus b into a minus b. Here I can write it as z minus square root of 3 into z plus square root of 3 into z minus I into z plus I. It is not defined at the points z is equal to plus or minus root 3 and z is equal to plus or minus I. At all other points in the complex plane, by quotient rule and product rule of differentiation, f is differentiable. Hence, analytic at each point where it is defined, that is f is analytic throughout the complex plane except for the singular point z is equal to plus or minus root 3 and plus or minus I. Differentiation formulas need to be applied only if the expression for f dash z is wanted. That is, when a function is given in terms of its component function uxy and vxy, that is uxy and vxy. Its analyticity can be demonstrated by direct application of the Cauchy-Riemann equation. Now, we have verifying analytic using Cauchy-Riemann equation. We have an example. That is fz is equal to, the question is cos hx into cos y, cos hx into cos y plus I sin hx into sin y. This is my fz. Here the component functions are, here we have uxy, it is equal to cos hx cos y, this is my uxy, cos hx cos y, and vxy is equal to the other one, that is sin hx sin y, because here ux, that is dou u by dou x is equal to sin hx cos y cos y, which is equal to Vy, and uy is equal to, that is dou u by dou y, which is equal to minus cos hx sin y, that is equal to what? Minus Vx. So, everywhere it is clear that f is entire. Next, we have a function fz is equal to uxy plus ivxy and its conjugate, or that is conjugate fz bar, which is equal to uxy minus ivxy, are both analytic in a given domain D. We have to show that fz must be constant throughout D. That is the function fz. Here it is fz is equal to uxy plus ivxy and fz bar, which is equal to, that we know, uxy minus ivxy. I have to show that fz must be constant. We write fz bar is equal to, that is fz whole bar is equal to uxy plus I into vxy. Where we have uxy is equal to uxy, this is our capital U and capital V. So, capital uxy is equal to uxy and capital Vxy is equal to, I can write capital Vxy is equal to minus Vxy. Equation number 1. Because of the analyticity of fz, the Cauchy-Riemann equation ux is equal to uy is equal to minus Vx, that is equation number 2, hold in D, and the analyticity of fz conjugate in D tells us, using the Cauchy-Riemann equation, that ux is equal to vy, that is ux is equal to vy and uy is equal to minus Vx. Equation number 3. In view of relations 1, equations 3 can also be written as ux is equal to minus vy and uy is equal to Vx. This is our equation number 4. From 2 and 3, we have ux is equal to uy and ux is equal to minus vy, which on adding gives, we have 2ux is equal to 0, that is ux is equal to 0 in D. Similarly, subtraction involving corresponding sides of the second of equations 2 and 4 reveals that Vx is equal to 0. Now, using expressions 3, that is formula for finding f dash of z naught in terms of the partial derivatives, we obtain f dash z is equal to, that is f dash z is equal to, we can write this is equal to ux plus I Vx, which is equal to what? 0 plus I 0, which is equal to 0. And it follows from theorem 4 that fz is constant throughout D. Next, we have an example. If fz is equal to uxy plus ivxy as usual be an analytic function, then prove the following, that is uxy is equal to a constant implies, that is uxy a constant implies that fz is a constant. Second one, vxy is equal to a constant implies fz is constant. Similarly, we have vxy is a constant implies fz is constant. Next, mod fz is equal to a constant implies fz is constant. Next one, argument of fz is equal to a constant implies fz is constant. That is first one uxy, next one vxy is a constant implies fz is a constant. The third one we have mod fz as a constant which implies fz is a constant. Next one argument of fz equal to a constant implies what? Fz is a constant. Solution. Uxy is equal to a constant implies dou u by dou x is equal to 0, dou u by dou y is equal to 0. Then using Cauchy-Riemann equations we obtain what? Dou v by dou x is equal to minus dou u by dou y which is equal to 0, and dou v by dou y is equal to dou u by dou x which is again equal to 0. Hence, v is also a constant. Therefore, our fz is equal to uxy plus ivxy is a constant. Second one proceed as similar as first one. Third one we have mod fz is equal to 0. Third one, mod fz is equal to 0. That means fz is equal to 0, a constant. Hence, it remains to consider the case when mod fz is equal to a non-zero constant. That is, mod fz is a non-zero constant implies that mod u plus iv is a constant, which implies what? We can write square root of u square plus v square is a constant. That is, this we can write u square plus v square is a constant. Differentiating, we have u square plus v square equal to c. Partially with respect to x we obtain that u into dou u by dou x plus u into dou u by dou x plus v into dou v by dou x equal to 0. This is our equation number 1. Also differentiating, u square plus v square is equal to c partially with respect to y. We get u into dou u by dou y plus v into dou v by dou y is again equal to a constant 0. This is our equation number 2. Using Cauchy-Riemann equations, the equation 1 and 2 gives u into dou u by dou x minus v into dou u by dou y is equal to 0. And u into dou u by dou y plus v into dou u by dou x is equal to 0. By multiplying these two equations by u and v respectively and adding, we get u square plus v square. Adding, we get u square plus v square into dou u by dou x is equal to 0. Since mod fz is a non-zero constant, we have u square plus v square is a non-zero constant, and the above implies dou u by dou z is equal to 0. By a similar process, we can show that dou u by dou y is equal to 0, dou v by dou x is equal to 0, dou v by dou y is equal to 0, all equal to 0. Dou u by dou y again equal to 0, dou v by dou x is equal to 0, and dou v by dou y is equal to 0. Hence, u and v are constant, and hence fz is a constant. As in the previous example, we consider a function f that is analytic throughout a given domain D, and such that the modulus mod fz is constant throughout D. We prove that fz is a constant throughout D. For that, we take mod fz is equal to c for all z in D, where c is a real constant. Case 1, if c is equal to 0, it follows that fz is equal to 0 everywhere in D. That is if C is equal to 0, I have Fz is equal to 0 everywhere in D. If C not equal to 0, case 2, using the fact that for a complex number W conjugate is equal to mod W square, we have Fz conjugate is equal to mod Fz square, which is equal to C square. Fz conjugate is equal to C square, and this tells us that Fz is never 0 in D, for otherwise C equal to 0, a contradiction. Hence, we can divide this equation number 1 by Fz and obtain Fz conjugate or Fz bar is equal to C square by Fz for all z in D. The numerator and denominator of the quotient on the RHS of this equation are differentiable throughout D. Hence, by quotient rule of differentiation, it follows that Fz conjugate is analytic everywhere in D. Now, the analyticity of Fz and Fz conjugate throughout D implies, using that example, that Fz is constant throughout D. Fourth one, we note that argument of Fz is equal to tan inverse V by x. Tan inverse V by not x, V by u. Hence, argument of Fz is equal to C, a constant, implies that tan inverse V by u is equal to a constant C, which implies V by u is equal to tan C, which is equal to, that is, u is equal to, we can write u is equal to V cot C. Setting cot C is equal to k, we see that u minus kV is equal to 0 unless V is identically 0. But u minus kV is the real part of 1 plus ik into u plus iv, which is equal to 1 plus ik into Fz. Hence, it follows from the first one that 1 plus ik into Fz is a constant. Hence, we can conclude that Fz is also constant. Next, we have an example that find an analytic function whose real part is e raised to x into x cos y minus y sin y, and which takes the value e at z is equal to 1. If the desired function is Fz is equal to uxy plus ivxy, then we have uxy is equal to we can write uxy is equal to e raised to x into x cos y minus y sin y. Hence, dou u by dou x is equal to, that is differentiating with respect to x, we have e raised to x cos y plus e raised to x into x cos y minus y sin y. Which is equal to, I can write this as e raised to x plus x e raised to x into, that is I am taking this cos terms together, into cos y minus y sin y e raised to x. Equation number 1. Similarly, we have dou u by dou y also. Dou u by dou y is equal to minus x into e raised to x into sin y minus e raised to x into sin y plus y cos y. That is minus x into e raised to x into sin y minus e raised to x into, in the brackets we have sin y plus y cos y. This is equation number 2. Using the Cauchy-Riemann equations, dou u by dou x is equal to dou v by dou y. This equation 1 implies that dou v by dou y is equal to e raised to x plus x e raised to x cos y minus y sin y into e raised to x. This is equal to what? Dou v by dou y. Integrate, this is equation number 3. Okay. Then integrating 3 with respect to y, we have this v is equal to, integrating this equation we get v is equal to e raised to x plus x e raised to x into sin y minus e raised to x into minus y cos y minus integrating 1 minus cos y into dy plus hx, which is equal to e raised to x plus x e raised to x sin y, e raised to x into, that is e raised to x in x plus x e raised to x into sin y, first term, plus e raised to x into y cos y e raised to x into y cos y minus e raised to x sin y, and the last term is plus hx, a function of x, which is equal to, simplification we get, which is equal to x e raised to x sin y plus e raised to x y cos y plus a function hx. This is our equation number 4. Differentiating with respect to x, the above yields dou v by dou x is equal to we can write dou v by dou x, which is equal to x e raised to x sin y plus y cos y e raised to x plus e raised to x sin y, then what? Plus h dash of x. Equation number 5. Using the Cauchy-Riemann equations, dou u by dou y is equal to minus dou v by dou x. Equation number 2 implies that dou v by dou x is equal to x e raised to x into sin y plus e raised to x into sin y plus cos y cos y. The LHS of 5 and the 6 are the same, therefore RHS of them are also same, that is x e raised to x into sin y plus y cos y e raised to x plus e raised to x into sin y plus h dash of x is equal to x e raised to x into sin y plus e raised to x into sin y plus y cos y, h dash x is equal to 0. That implies h dash x equal to 0, which implies that h of x is equal to c, a constant. Hence, equation number 4 implies v is equal to x e raised to x sin y plus e raised to x y cos y plus c. That is, hence fz is equal to u plus iv can be written as fz is equal to, instead of u I can write e raised to x into x cos y plus I sin y plus y into minus sin y plus I cos y plus ic. That is equal to e raised to x in, that is equal to e raised to x into x e raised to x plus I y into in the brackets we have cos y plus I sin y, what, plus ic. This is equal to e raised, I am taking e raised to x outside, that is e raised to x into x e raised to iy plus iy into e raised to iy plus ic. That is e raised to x into, this I can write as e raised to x into x plus iy into e raised to iy plus ic. That is e raised to x plus iy into x plus iy plus ic, or I can write this is equal to e raised to z into z plus ic. It is equation number 7. By the given condition, when z is equal to 1, fz is equal to E. Hence, from the equation number 7, we get E is equal to f of 1, which is equal to E plus IC. Hence, IC is equal to 0 implies C is equal to 0. Hence, we have fz is equal to z e raised to z. Next, we have an example that if a function is analytic, show that it is independent of z bar. For that, let the function be w is equal to fz. It is as usual uxy plus ivxy. To show that it is independent of z bar, we have to show that dw by dz bar is equal to 0. For that, let z is equal to x plus iy and z bar is equal to x minus iy. Therefore, x is equal to I can write x is equal to z plus z bar by 2 and also y is equal to z minus z bar by 2i. Regarding x and y as functions of the two variables z and z bar, we have the following partial derivatives. That is, dou x by dou z bar is equal to 1 by 2 and dou z by dou z bar is equal to minus 1 by 2i. Now, differentiating the first equation with respect to z bar, we have dw by dz bar is equal to dw by dz bar, which is equal to dou u by dou z bar plus I into dou v by dou z bar. Equation number 2. Now, applying the chain rule, we have dou u by dou z bar is equal to dou u by dou x into dou x by dou z bar plus dou u by dou y into dou y by dou z bar, which is equal to 1 by 2 times dou u by dou x minus 1 by 2 I into dou u by dou y. And again, dou v by dou z bar is as usual dou v by dou x into dou x by dou z bar plus dou v by dou y into dou y by dou z bar, which is again equal to 1 by 2 into dou v by dou x minus 1 by 2 I into dou v by dou y. Putting these values in the expression 2 of the theorem 4, we obtain dw by dz bar, dw by dz bar, which is equal to 1 by 2 into dou u by dou x minus what? Dou v by dou y minus 1 by 2i. We have 1 by 2i into, in the brackets we have dou u by dou y plus dou v by dou y, which is equal to 0 using Cauchy-Riemann equation, which is equal to 0. This is by using Cauchy-Riemann equations. We have ux is equal to vy and uy is equal to minus vx. Hence, w is independent of z bar. So, in this session, we discussed a lot about analytic function and rules for analytic functions and done so many examples. Next time, we will discuss some other topics regarding this complex analysis. Till then, take care.